Hi everyone, we will start in a few minutes. In the meantime, I will put up a link to a folder with the presentation. One moment. So the presentation is a really large file, so I split it up in different slides. It's really beautiful. The slides in there are really beautiful with a lot of videos. So feel free in the meantime to check them out. And if you cannot open in preview mode, you would need to go ahead and download the presentation in order to see them on your device. But it's really worth it because there are amazing videos in there that Dr. Cohen made available for us. So, and feel free to share the room and people that think they would like it. And the paper link I will share in the chat. But I would really go through the videos. They're amazing. So hi Elizabeth, Ken, Sue. I did my best to split it up. I know it's a little bit confusing, but in the title you see the different numbers of the slides. So so for people that don't have a good internet connection and can download stuff, I split up the slides. So I hope it works. And again, it's an amazing presentation with a lot of very cool videos. So it's really worth it to go through the trouble and download it. So and I think,
Hey.
hi Victoria, how are you?
Hi, good, thank you. It was just snowing here.
Oh wow, really?
Yeah.
Nice, I love
Mm,
snow.
mm, mm. How are you?
Elizabeth? Yeah, I mean, I checked everything. It's a safe file, and I know you can. Some of them you can view in preview mode. Like some of the, like 1 to 20, for example, shouldn't be a problem, and so on. But I think a few of them are still too large because the videos are just large. But it's worth it. But I tried my best to downsize the slides to compress the images, but the videos are really, that would be a shame to like make the quality bad. So yeah, I'm sorry, there was no way I could. I have in the end one slide per file, but it's still too big. So yeah, I'm sorry, but it's worth it. You find downloading it. It's a save file. We checked it. Go ahead, Victoria. Sorry, I was just answering the question.
Oh, goodness, no, I just came in. I didn't know it was happening before I arrived. So, yeah, exciting about the files that we're getting in here. Lots of cool info.
Yeah, I mean, the videos are really beautiful and really interesting. So I think it was worth going through the trouble. And yeah, our guest speaker is on Clubhouse. He texted me and I sent him the link to join again. I hope he's figuring it out.
Katrina, do you have the videos that you can upload there to the folder in Google? Hi guys, how are you?
Yeah,
Hey,
sure.
Daniel,
It's in the.
welcome.
Hi, Daniel. How are you?
Hi. Nice to meet
Yeah, it's in that drive that I shared that I pinned
you.
there.
Okay, I don't see the videos because I think
They
Google.
are in the PowerPoint embedded.
Oh,
The
inside the
files.
PowerPoints. Okay.
Yeah,
Yeah, got
yeah.
it. Got it. Yeah, yeah.
So it was one. So it was one PowerPoint presentation
I
that
see.
was over a gigabyte.
Yeah.
So I split it up as much as I could, but some slides have 3 videos, so they are
Yeah.
still too big. So some of them, most of them, you should be fine in preview mode, like to just see the slides on the screen. But maybe a couple you have to download to see the
Got it.
videos.
Yeah. When you upload videos to Google Drive, and then you play them back, Google will like recode them on the fly for making more efficient. But I don't think that will work for the PowerPoint image. But I see the complication. Okay. Thank you. Yeah.
Yeah, yeah. I did my best, but it's worth it to just, it's really cool videos, and will be an interesting talk. Let's see. I pinged Dr. Cohen in, and he texted me. Let's see. Well, he should be here any minute.
Well, he'd still be early.
Yeah, it's still 2 o'clock.
He's
I'm really glad he made the time to come to present this. And I'm so happy for him. I don't know, you like snow, Victoria? That you have snow already? I wish we had snow.
yes, and it's the second time it's not. It wasn't predicted. It just I was going out on a walk. I grabbed my umbrella, and then suddenly it's so quiet and it's snowing. It's really pretty, but
Yeah.
not sticking. So it's just novelty snow, decorative snow.
Ah, okay. Well, it's so funny.
Hmm.
So, let's see. Hmm. I don't know why there would be an issue to join.
Is he possibly in his own room?
Yeah,
Are
I'm
we?
trying to find him.
Did he open his own room? You see him on the app currently.
Yeah, he is on the app. Did I send him?
He's
Yeah.
out making friends.
Hi, Eli. How are you?
Hey, Katerina, finally surmounting some software challenges to run simulations that have been bedeviling me.
Well, it sounds interesting, though.
Really, no, it isn't. The interesting part comes now that I have surmounted those challenges.
Oh, okay. Then one day we have to make a room about that. About what you're working on.
There will be a few. It's the Lagrange point one Earth Sun Lagrange point one Sun Shield.
Oh, yeah. Yeah, send me a link when you have it. I'm definitely coming to hear all about it. I don't know. He texted me, but I can't see. He's not answering back now.
That was a question.
Yeah, go ahead. Sorry.
What is the maximum change of curvature? What does that mean? In the slide that has the picture of the Millie robot that looks like a little dragonfly.
I didn't make the presentation, but Tai is here, so he will answer everything because he will present
Okay.
it. Thank you,
Oh,
Elizabeth.
welcome, Itai.
The unmute button is all the way on the bottom right, and there's a little mic. Yep, perfect.
There we go.
Sorry that
Ah.
was it a problem to come on?
No, I think once I got your note, it was fine.
Okay. Okay, perfect. I'm glad that worked out. So, yeah, as I said, for the audience, I split up the file in a bunch of files. But when you present, you can just look at your file and mention maybe the slide number sometimes, so people can then click on the next file in the folder. I think that should work fine.
Sure. And can you say if the videos work when people click on them?
Yeah, for me they worked in the
Okay.
PowerPoint, so it should work for everyone then. If not, I think, everyone should by now feel comfortable to tell us that, that something is not working or they can see something.
Great. And
Okay, I'll start by introducing you if that's okay, and then
perfect.
Victoria usually asks like a couple of interview questions to start off, and then we'll go into your presentation if that's okay with you.
Sounds good.
Perfect, thank you. And for the audience also, I put the paper that came out in Science, the link in the chat. And yeah, as I said, the presentation files are in the folder that I shared on top. So welcome everyone to Science Society, and of course a special welcome to you, Itai Cohen. Dr. Cohen did his bachelor in physics with summa cum laude, and in 2001, he went to the University of California at Los Angeles, and then he did his PhD at the University of Chicago in physics and singularity formation in fluid interfaces. And he's presently professor in the Department of Physics and Laboratory of Atomic and Solid State Physics at Cornell. He won many different awards, like there's a long list of many awards, and the latest one I believe was in physics and astronomy, van der Waals visiting professor at the University of Amsterdam. In 2021, Rosie and Max Veron visiting professorship at the Weizmann Institute. And it's such an honor having you here presenting this so interesting work of yours. And as I said, Victoria will ask you a few questions before we start. So I'll hand over the mic to you, Victoria. Thank you.
Thank you, Katarina and Itai. Dr. Shah and Katarina and I are so happy to welcome you here to Science Society today and give you the mic and have you get on with your talk. And before we do, I would like to have you share a bit of yourself with our listeners today. And so my question for you is, if you can maybe share with us what your unique connection is to science, meaning if you can remember sometime in your childhood or excuse me, I'm sorry about the noise, I'm walking and a truck is driving by. If you can think of a time that you felt that connection to science, that was yours, that was, maybe ignited the spark.
Yeah, I guess for me, I've always been around science. So my dad was a biologist, and my mentor, Jacob Islatashvili, was a prominent person in my life as a young kid. But I don't think I really got the bug until I discovered something, and that was during my undergraduate degree at UCLA. And we were studying this material called triphenyl phosphite, and we discovered a liquid-to-liquid phase transition. And that moment of discovery was just intoxicating, super interesting, fun. At that moment, I was the only one who knew what the heck this thing was doing. It was the secret that I was about to share with the world, and it was fantastic. So to me, that's really where I caught the science bug, where I finally understood what it was to do science, making those discoveries.
Thank you. That's exciting. It's different for everyone, and there really does seem to be a unique connection for everyone. So it's great to be able to hear, and we remember these things. So can you please take us from that point of, initial spark or whatever we want to call it, to your place now where you're doing your current work that you're going to present to us?
Yeah, I mean, so that was sort of my first discovery, and then I went to Chicago and did a PhD. I was very fortunate to have a very supportive mentor, Sid Nagel, who helped me sort of get up to speed. And what was really fantastic about Sid was that, he taught me how not to be afraid. Every conversation that we would have would start with like, "What the fuck do I know about dot dot dot?" And then he would proceed to tell about dot dot dot, and somehow it sort of gave me this idea that we're all just trying to figure this out, and it's not really that there's this sort of edifice that we have under us and that we're sort of building this thing brick by brick, but you're sort of starting somewhere in the middle and trying to feel your way around and get a footing that you can then use to move things forward. So this feeling of not you know not necessarily needing to know everything before you make a discovery, that was really important to me, and that has sort of followed me to my career at Cornell. Today in my lab, we study microscopic robots. I have zero training in robotics. Uh, I have barely the training in the material science that it takes to do the robotics that we're doing. And yet, with the beautifully collaborative and well-equipped environment here at Cornell, we can make those kinds of amazing things happen, despite coming at this problem from a place that's not traditional. Um, Other things that we do in my lab include studying insect flight. To use Sid's phrase, what the fuck do I know about insect flight? Not very much, but we're still able to make contributions because, again, the students are phenomenal. The techniques, that we're bringing to bear are new and interesting. And so we're able to make contributions at what I hope is a pretty high level to the field. And that sense of adventurism, that sense of, you know, uh, if you're curious about it and if you have a good idea about how to contribute to solving these problems, not feeling inhibited about the fact that you may not have a background in this, but really um, taking that leap into the unknown, that's been very exciting for me and a very fun and fruitful way of pursuing science.
Sorry, I had to navigate back to the microphone. Something that was particularly interesting about that, all that you shared, was when you said that you didn't have a background in those disciplines, and it just speaks to the interrelatedness of things. That what you described, you had the structure and the backing and the curiosity and the methodology at Cornell, and it's your it's that strength that moves you forward, and so you can pursue your work. And so at this point, I will pass you the mic and just let you know that we are here to moderate the room, and any questions that might come up. Sometimes listeners will put a question in the chat and we can share those with you, or have Q&A following your discussion or along the way, whatever you'd like. But thank you so much for being here, and the mic is yours.
Okay, thank you. So I'm working off of the PowerPoint file that hopefully was being shared with everybody. And what I'll do is I'll call out the slide numbers where I can, and we'll go from there. The talk is supposed to be roughly 20 to 30 minutes, and then we can have questions after that, but I also encourage people to put questions in the chat, and hopefully, Katerina, you can monitor that, and please interrupt when something is not clear or if I'm using jargon or anything like that. So the story I want to tell today is about microscopic robots. So I'm starting with slide number 1 here. And if we think about this problem of microscopic robots, go on to slide number 2, it really starts with this famous lecture given by Richard Feynman called There's Plenty of Room at the Bottom. And in this lecture, Feynman predicts the miniaturization of electronics and tells us that the transistors are going to become smaller and smaller. And indeed, 50 years of Moore's law have brought about this vision of microscale electronics. Today, we can build entire cities on the scale of nanometers, and these cities, perform beautiful computations and that power our iPhones and computers. And it's really been amazing to watch that process of miniaturization. And it's also interesting that we're now sort of coming to the end of that as the feature sizes reach atomic length scales. Now, in that same lecture, Feynman also talks about the miniaturization of machines. And in this capacity, I would claim that we're still quite primitive in terms of the machines that we can make at the microscale. And this is the part that I want to think a little bit about. And so if I go on to slide number 3, let me just point out that in the science fiction literature, this problem is solved. And we now have, nanoscopic robots that can make Iron Man's suit. The Borg know how to manipulate things on the nanoscale. There's the magic school bus that can, move through our bloodstream. But the question that I want to ask is, are there really any real microscopic robots? And moving on to slide 5 and 6, the answer is sort of. So if you take a look at active matter, these are little particles, if you're looking at the videos on slide 6, that can self-propel. So these are autonomous in the sense that they're moving on their own, but they're quite simple. They don't really do anything other than move, they don't sense, they don't compute. We have other structures. In slide 7, you see some micro machines that can undulate. They have magnetic patterns embedded in them that allow you to manipulate them in some way. So these are more complex, but you have to externally control them. And more broadly, I would say that we now know how to make machines in the sense that we know how to make their body plans, but they don't really have brains yet. So moving on to slide 9 and then 10, what I'm thinking about when I'm thinking about microscopic robots is trying to combine the brains of the robot, so some sort of microchip that's going to allow you to have autonomy and control with actuation, which is the legs. Now, the brains of these robots is something that we already know how to do. So as we've talked about Moore's law, and if you go to the next slide, titled Optical Wireless Integrated Circuits, these are some of the circuits that have been made by my colleagues, Paul McEwen and Al Molnar. And the devices that you're seeing here are very simple sensors. So at the bottom right, you're seeing a voltage meter. There are 2 pads called input that allow you to measure the voltage between those 2 pads. There's a bank of photovoltaics. There's a MOSFET transistor, an LED, that registers out the voltage difference between those 2 pads. So this is a very simple sensor, and it's connected to the silicon wafer with these 2 tabs, these release tags. So if you ever played with model airplanes, these are the same kinds of tabs that you might get the plastic pieces in that you would then assemble and glue together. So you can take these little devices and remove them from the wafer. And if you move to slide 12, I'm comparing the devices that we make on the right with the kinds of things that others have made. So at the University of Michigan, people make things like the micromote. At Berkeley, they make things like the smart dust. These are chips that have been sort of bonded together, and they're the kinds of things that you might put in a pill that you would swallow that would take pictures of your gut. And on the right, you're seeing the devices that we make. And if you click down a couple of times, you'll see that the devices are so small that you can't really see them on a normal penny. But if you zoom up to the Lincoln, not the one that's on the face of the penny, but the one in the Lincoln Memorial, it's sitting there right on the chest of that Lincoln at a scale of about 100 microns. So it's super tiny. Now, small doesn't necessarily mean better. The devices on the left have a lot more computational power. But small does mean that you can make millions of these on a single wafer. They're very cheap, and they could be dispersed like dust on different surfaces. So moving on to slide 13, someday you'll look down at your finger, and if you notice that little speck of dust, that'll be one of these devices measuring the pH of your finger. And these devices will then flash, you'll be able to use a cell phone to flash at them, and they'll tell you your skin is dry, you should use this cream, and things like that. So the brains is actually the easy part. We know how to miniaturize the brains, and we know how to remove those from the wafer. The hard part is the legs. So slide 14 illustrates that. It sort of highlights the actuators that are making these microscopic robots' legs. And that's actually the hard part that we at least didn't know how to do. And the problem, moving on to slide 15, is that you can't just take a three-dimensional machine and shrink it down in size. You can't take a jet engine and make a microjet engine. Instead, you have to do something more akin to what's on the next slide, where you have origami robots. And the idea here is this is a macro scale version. So this is out of Rob Wood and Eric Demain's labs. They printed a 2D robot, they slapped a couple of batteries on, and then got the robot to fold itself and walk off the page. And the idea is to do something similar to that, but now at the micro scale. So could something like origami enable machines at the micro scale? Is that a paradigm that we can adopt? And the idea is, if you look at slide 18, to steal fabrication tools from the electronics industry, essentially build around the microchips in 2D, and then fold the three-dimensional structure that you're trying to actuate to get your three-dimensional robot. Okay, so that's the idea. Maybe I'll pause to see if there are any questions. Any questions, Katerina?
So far, no questions. Thank you.
Okay. All right. So we had to learn how to do this. So the next slide, you'll see a picture of the nanofabrication facility at Cornell. It's one of the premier research facilities in the United States, and part of the nanofabrication institutes that are spread all over the country. And in slide 20, you're seeing some of the devices that we've made, some of the materials that we've been able to make. And by we, I mean the students. So on the very top left, you're seeing a single sheet of graphene. The video is a single sheet of graphene that's being stretched. It's been cut and patterned in the same way that you see that Kirigami toy on the upper left. And the idea is that on the atomic scale, right, this is just atomic scale origami. We've also learned how to build things using atomic layer deposition. Essentially, you can think of that as a technique where you spray paint one atomic layer at a time on a surface. And then we can have a release layer, which allows us to grab that film. In this case, the middle shows 5 nanometers of glass decorated with these polymeric posts, sort of acts like a sheet of paper. On the bottom, you see 3 images of a metamaterial sheet that is cut up so that you can stretch it in the middle frame and then bring it back to its original configuration in the rightmost frame. So these are all the kinds of papers that we can build. And on slide 21, the question that I'm posing is, okay, but how do you fold them, right? Like, you know, it's one thing to make atomically thin paper, but you can't really shrink your graduate students to the scale of atoms and get them to fold the paper. Somehow you're going to need to do something more akin to what's on slide 22, which is to have the paper fold itself. Basically design a pattern that you build in beforehand, and then somehow get the paper to do the folding and create the pattern that you want, as sort of illustrated by this beautiful video by Sifo Mabona. So how do we do that? On the next slide, you can see our atomically thin paper folding itself. So this is the work of Mark Miskin, Qingpin Liu, and Wei Wang. What Mark did here was he took an electrode, he picked up a little ribbon of our paper, and by essentially adjusting the voltage knob, he can get the ribbon to curl up and uncurl at will. So how does this work? On the next slide, you'll see a video showing that we make these out of 7 nanometers of platinum, capped on one side by an inert material. We then fabricate the actuator and put it in solution. If you apply a voltage to the platinum, then ions from solution adsorb onto the platinum surface and create a stress which bends the actuator. If you now apply the opposite voltage, you can drive those ions off of the actuator and it returns to its original shape. And by putting rigid elements on the actuator, fabricating rigid elements on there, you can constrain the bending to occur in folds. And so this is the way that we get the sheet to make its own origami pattern that it self-folds. On slide 25, I'm showing that you can also get these things to give you shape memory. So the idea here is that if you apply enough voltage, a high enough voltage, you can actually oxidize the surface of the platinum, and that creates a barrier for the oxygen atoms to come off of the platinum. And so you have to go to negative voltages before they come off. So that hysteresis loop that you're seeing on the right means that you can get 2 different curvatures, two different voltages for the same curvature, and that gives you shape memory. So on slide 26, I'm showing that you can touch the electrode down, close the gripper, remove the electrode, it stays closed, touch the electrode down and open the gripper, remove the electrode, it stays open. So that's what we mean by shape memory. You can retain the shape even when the system is untethered and disconnected from the voltage. So on slide 27, I'm showing a plot of the maximum change of curvature as a function of actuation voltage. And the thing that I want to get across here is that what you're hoping for is to create devices that can have a very large maximum change of curvature and do it under very small voltages. And the devices that we make are in red, they're the very top. They have radii of curvature that are submicron, and they can be actuated at voltages less than a volt. The purple diamond is also our work, slightly higher radii of curvature and slightly lower voltages. That's the one where you don't do the shape memory. So you just do electrochemical actuation. Those are the volatile Cs. And this is important because if you look at the kinds of devices and machines that you want to manufacture, if you're looking at robots, you're really looking at the bottom third of this diagram here in terms of radii of curvature. And if you're looking to make milliscale robots like the RoboBee, you're somewhere in the middle. But if you want to make microscopic robots, you really have to have actuators whose radius of curvature is on the micron scale or smaller. Otherwise, your basic building block is too big to make anything that's going to be microscale. So on to slide 28, you're seeing videos, if you play them, of a hexagonal fold, a Mura-Ori, which is a canonical origami fold, and the world's smallest duck. These are devices that can fold and unfold as a function of the voltage that we apply, and they're just beautiful. So slide 29 shows SEMs of these devices. The bright yellow shows you the platinum films capped on one side, either the top or the bottom, to give you mountain or valley folds. The darker yellow panels are silicon dioxide. It's about half a micron thick. And this is origami at the atomically thin scale. And the duck on the left graced the cover of Science Robotics in March of 2021. And you can see, again, just this very, very thin, bright yellow part. That's the 10 nanometers of platinum that we fabricate. Now, so maybe I'll, again, just break for a second to see if there are any questions.
Not so far in the chat. Does anyone else here have a question? Then please flash your microphone. No, I think you're explaining everything really well, and the videos are very beautiful. So everyone is probably mesmerized by the tiny origami.
Okay, I keep going. Okay, so as amazing as this origami bird is, it still has that wire hanging out on the left-hand side. That is the wire that we use to apply the voltage to the platinum film. And so we can try to get rid of that. So if you go to the next slide, 31, you'll see that you can attach photovoltaics to these actuators. So on the right, I'm showing you an SEM of a photovoltaic attached to one of these actuators. And if you play the video associated with this slide, you see that if I shine light on the photovoltaic, I can get the actuator to wave hello. So this is our first ever working device. It's our hello world. Admittedly, the hello is pretty slight, kind of like the Queen's wave. We're looking for more of an American at a football game, but it's a start. And if you go to the next slide, now you can try to go and get really ambitious. You make a photovoltaic for the front legs, photovoltaic for the back legs. You have attachments for both of those. In the next slide, I show that we can make bajillions of them on a wafer. You can add pads to restrict the bending to occur where you want it to occur. And on the next slide, you'll see a movie of one of these devices that's been released, flexing its muscles. This device we lovingly call Brobot. We shine light on his front photovoltaics, and he flexes his arms. He belongs on a beach somewhere with all of his chest hair. Now, okay, he's got some defects. The technical word for the chest hair is schmutz. We don't really want that there. His back legs have been ripped off. That's a problem. But you get the idea. You get the spirit of this. And if you work hard to fix all of these problems, then you can get the robot on the next slide. So slide 35, what you're seeing is a robot that is 40 microns by 70 microns by 2 microns thick. This robot holds the Guinness World Record for the world's smallest walking robot. The particles that you're seeing on the side in solution next to the robot are jiggling. That jiggling is Brownian motion. So this robot is at the absolute limit where any smaller and it would be Brownian. And the way it works is it folds itself up, and by shining light at the front photovoltaics and back photovoltaics, you actuate the front and back legs. And that allows this robot to essentially walk off the petri dish. So in that same spirit as the origami robot that Rob Wood and Eric Demain made, this robot is doing the same thing, but now at the micron scale. Now, as amazing as this robot is, it is still just a marionette. So we have strings attached to it. If you go to the next slide, our strings are lasers that we point at the photovoltaics. And Mark had to painstakingly point a laser at the front photovoltaics to get the front legs to actuate, back photovoltaics to get the back legs to actuate, back, front, in a long experiment in order to get the video that you saw, that you just saw. So how do we do better? And we can do better by putting brains on board that direct the voltages automatically. So the way we do that is we collaborate with a commercial foundry called XFAB. So you can see that on slide 37. And on slide 38, I show XFAB gives us the transistors, capacitors, resistors, photovoltaics. And what we do at the nanofabrication facility here at Cornell is we add the actuators, the releasable devices, micro LEDs, all of the heterointegration that happens here on campus. And on the next slide, slide 39, you can see what one of these wafers looks like when it comes back from XFAB. These are hundreds of thousands of silicon brains that are essentially on this wafer to help us automatically actuate the legs of these robots. And the person who spearheaded the heterointegration of these brains with the actuators is Michael Reynolds. He's the lead author on the paper that, that we're essentially discussing. So if you go to the next slide, slide 40, you could see what some of these brains look like. And if you go to slide 41, you can see what one of them looks like up close. If you click down, you'll see that the blue rectangle is highlighting the photovoltaics that are used to power both the circuit and the legs. And the red square is highlighting the CMOS circuit, the brain of the robot. If you go to slide 42, you can see what this robot does. Effectively, it emits a voltage pulse at different timings. So there's a phase lag that's associated with each pin that you can connect up to. And so the idea is that you get these plus 0.6 volts or minus 0.6 volts actuations. And depending on the pin that you connect to, you get that at different phases in the clock cycle. And then the very bottom, you're seeing that we can hardwire which frequency we select in the device. So because this device is emitting essentially a clock signal, we call this clock bot. And on the next slide, slide 43, if you click down, you'll see all of the different fabrication steps that Michael had to go through in order to link up these electronics with the legs and bodies of the robots that he integrated. And so this is 13 photolithographic layers, lots of clean room hours, 20 tools, 11 depositions. A lot of work went into figuring this process out. And the thing that's beautiful about lithography is that despite all of that effort, now that we have the recipe, it basically can work every time. So you don't have to figure things out anymore. You can just go to town using this recipe that Michael has already figured out for you. On slide 46, I'm showing you an example of one of these. We call this robot PurcellBot. PurcellBot has two limbs on the right and on the left. The top and bottom are electrodes. And if you click down to slide 47, you get an illustration of how PurcellBot walks, essentially by moving the legs underneath the closer to or farther away from the center of mass. you can change the amount of friction on the tip of the leg with the surface. And if you go to slide 48, you can see a video of PurcellBot walking across a fairly slippery table. This is a Lego model of PurcellBot that Michael built. And the idea is that PurcellBot does something like this, but only at the micro scale and immersed in a fluid. And that's what you're seeing on slide 49. If you play that video, you can see PurcellBot crawling across your screen in real time. And now no one's shining any lasers. All of the controls are on board. The circuit does everything on its own. And this thing just, you put it in sunlight and it walks autonomously. No user necessary. We can do other things. So if you go to slide 50, you'll see an ant walking across your screen. Ants are hexapods. They have 3 legs on each side. And if you build a robot with 6 legs, a hexapod robot, depending on the timing that you actuate the legs, you can get different gates, different locomotory gates. And so in this particular case, in slide 52, we're going to choose a gate called a tripod gate, where 3 legs are actuated at a time. All the legs labeled 1 are actuated at one moment, all the legs labeled 2 actuated at the next moment. And by cycling through, you can get this thing to move across your screen. Now, slide 53 is a movie of Antbot walking across your screen in real time. And again, we're doing nothing to this robot except shining light on the whole substrate, on the whole arena, if you will, to get it to locomote across our screen. On slide 54, you'll see an image of Antbot before it's released. And again, this was on the cover of Science Robotics in September. We also made a device that could receive commands. So on slide 55, you'll see a microchip. And if you scroll down, you'll see where we have the optical receiver and the shift command that we can send the optical receiver. The idea is that by sending it a bunch of light pulses, you can give it a command, in this case, to shift its frequency from 2 to 4 hertz. And because this robot responds to commands, we call it DogBot. And if you go to slide 56, you'll see a video of DogBot moving across your screen. And it moves initially with a frequency of 2 hertz. And then when it gets the shift command, you'll see it start to move at twice the frequency, 4 hertz. On slide 57 and 58 and 59, let's see, all the way through 61, I'm kind of telling you about all the various things that we can now start to think about now that we have these capabilities. So first, we can build 100,000 of these robots on a single wafer. So the world's sort of record for, a university swarm is something like 1,000 robots by Michael Rubinstein. The Olympics in Tokyo had 5,000 drones making up the world in the opening ceremony, if you saw that. Now we're going to be able to make 100,000, just blow that number completely out of the water. And the question is, how do you even interact with 100,000 robots? Talking to each one separately is going to be very time consuming. And so you're going to want to start to think about how you organize signals both from the outside world to the robots, from the robots to each other. All of those sort of dynamics become really interesting as a research problem. You're going to start to be able to manipulate environments, do environmental cleanup, but now at the 100 micron scale. You're going to start to be able to make biomedical applications. You're going to work on trying to integrate things like sensing, communication, memory, new actuators that might be stronger or more efficient. All of these things are now possible and are being worked on by the teams here at Cornell. And in the same way that Marvel has its cinematic universe, on slide 63, I propose that Cornell it has a rapidly expanding microsystems universe of its own. And on slide 64, you can see some of these devices. We have chips that have become quite sophisticated, these neural motes on the upper left. We have been creating artificial cilia out of these actuators. I'll tell you a little bit about that. We have the microscopic robots that I just told you about. We have the robotic metamaterial surfaces. These are robots that are essentially a complete metamaterial and have distributed control. We have bubble rockets and even companies that are being spun off with these technologies. So on slide 65, I'll tell you a little bit about some of the things that we're doing on artificial cilia. On slide 66, you can see what our artificial cilia look like. They are these platinum actuators, these surface electrochemical actuators, and we just make carpets of them. And on the right is an SEM of some subset of the sample. On the next slide, what was that? 67, you can see them in action. We're putting a probe down and oscillating the voltage to get these to pump fluid. In this case, the fluid is doped with some colloidal particles, and you can see the little dots moving up. Those are the colloidal particles. And so these things pump the fluid in one direction. And what that means is that if you can pattern your array, you should be able to create flows in any direction. So on slide 68, you can see work that we did in collaboration with Ivan Tansjevic and Eric Lauga, where we put these arrays into square patterns. And the upper left, you can see an array where we are essentially activating the outer cilia on the left and the right, and the inner cilia on the top and the bottom. And by doing that, you can create an extension flow. And the image in A, the main image in A, is a trace of all the colloidal particles moving through or being pumped by the cilia. In B, what you're seeing is that same trace on the bottom. Those are experiments. In the middle is kind of a wedding cake geometry of the flows being simulated by Ivan and Eric. And on the top is the depth average simulation, which looks very similar to the experiment. And so by actuating different arrays in these square configurations, for example, in C, we create a source flow. So in this case, fluid is moving outward on the surface in all four directions, which means that it's being pulled from the third dimension downwards. We can create transport flows. So in D, you're just moving the fluid from one side to the other, turning flows in E, and so on. So these are elementary flow geometries that you can then connect up. And in 69, slide 69, you can see an array that we built up of these that can essentially produce arbitrary fluid trajectories within the same microfluidic device. And so here, you can, again, just pump your fluid in any way you choose. You can circulate it, have it split up and rejoin, as you can see in E, have two separate flow geometries like you can see in B, and so on and so forth. And we even, if you look at slide 70, we've coupled these to these these actuators to fibers. So we have a project that we are working with the group of Xiaoting Jia in Virginia Tech, where she can have fibers that can have electrical wires in them, so on the order of 100 microns. And so the vision is to connect some of these robotic actuators to these 100 micron thin wires or fibers, and then be able to, for example, create electrodes that you could insert into the brain in a folded up state, and then can extend them so that they can record from lateral regions in the brain without having to stick sort of 10 ice picks in different locations, creating a lot of damage. We're learning in slide 71 how to fabricate these actuators so that they work in air. In slide 72, we're learning how to make metamaterial devices out of the actuators. This is a project in collaboration with Nick Abbott, Tandaska Sazit, and Lisa Apsel. And here the idea is that you print the sheet, and by splaying the various panels, you can locally expand the area. And if you get inhomogeneous area expansion, that sheet will pop into the third dimension. And so you can create different Gaussian curvatures, different shapes, allowing the sheet to locomote across a surface and maybe wrap a source of some sort. So the bottom panel illustrates the idea behind this. And if you go to slide 73, these are experiments where we've now fabricated these. In slide 73, I'm showing you an experiment where we fabricated an inner region and an outer region. And by selectively actuating the inner versus the outer region, you can create the three shapes that you see on the bottom. The blue area is the part that's being actuated. And the green images on the bottom are confocal images of the sheets that we've made as they pucker up and form the undulations in 3 dimensions. On 74, I'm showing a video of one of these sheets locomoting across a surface. And again, the idea is to make these ever more sophisticated and able to adopt various shapes and various locomotory strategies. In slide 75, I'm showing you a robotic arm that we're envisioning. On slide 76, I'm showing a new actuator that we've been developing made out of palladium. And the idea here is that you can have palladium absorb hydrogen, and in contrast to platinum, which is only a surface, allows for surface oxidation, palladium allows for bulk absorption of the hydrogen, which means that you can create an expansion throughout the entire palladium layer. And that allows you to make the actuators thicker. It also allows you to make them stronger. And so on slide 77, I'm showing that these actuators, these palladium actuators in red, have some of the highest energy densities at the lowest voltages and the highest or lowest, smallest bending radii of any actuator on the market. So these things are amazing in terms of their material properties. They're really top of the line. And on slide 78, I'm showing the robotic arm that we've made out of these actuators. And you can see some videos in slide 79 of the swing, lift, and twist modalities of this robotic arm. And in slide 80, you can see the gripper in action as it is actuated. And each of these modalities, each motion of the arm or the gripping has its own pad on the bottom there that allows you to actuate it. So the idea is to hook these up through wire bonding to some sort of joystick, which you could then use to control the arm completely. And if you go to slide 81, that's just phase 1. And there's a lot more to come. And we're super excited about the various technologies, and we're in the process of forming a center on campus, really the Center for Microscale Robotic Systems. And in slide 82, I'm sort of talking a little bit about what this technology could enable at the 100 micron scale. And really, I'd like to point out that anything that you could do at the macro scale is fair game. You know, at the macro scale, we use robots to clean our surfaces, and the same thing could be done at the micro scale with robots that could sense contaminants and clean them either through changing the pH or killing bacteria off surfaces, you know, things like that. On the macro scale, we use robots to manufacture things. We could do that at the microscopic scale as well. Use them to manipulate their environment, carry cargo from one location to the other, shrink surgical tools by a factor of 10, and essentially allow for exploration of the microscale world in a way that really is different from the way that we do it now. right now we use microscopes to look from the top down, but building devices that have to function at the microscale really gives you a different experience or different understanding of what it is exactly that these bacteria and cells and microorganisms are doing at this scale, and what it takes to function and locomote and do all of those things at the submillimeter scale. So with that, on the next slide, I show all of the various people that were necessary, students, postdocs, and faculty collaborators that were crucial for helping us and collaborating on the work that I showed you today. And with that, I'll end on slide 84 with the various papers that we've written on these topics. And I'd be happy to take any questions or answer anything that was unclear in the presentation. So thank you.
Well, thank you so much. This was such an amazing presentation. And while I was splitting it up, I was really looking forward to your talk. And it's amazing how many different types of movements you can do, and on this tiny scale. Like one of the examples you showed was probably for monitoring neurons, and the micro robots with the cilia type of movement fluctuation. That the immediate thought is, of course, let's say keeping arteries clean and so on. Is that maybe something that's quite straightforward, what you could try? Like, what is the thing you would think will get like the earliest application, either in some
Yeah,
biological question or medical? Thank you.
yeah. I mean, so some applications that we're thinking about include putting active optical elements at the ends of fibers. Those I think are really ripe for applications. There's a lot of imaging technology that can be done with multi-mode optical fibers. And we think that by adding mechanical elements on their surfaces, we can do quite a bit to improve those. And along those lines, thinking about medical surgical tools that are at the ends of fibers, it really boils down to how big of a diameter do you want the device going into an incision or up some tube or artery as it's cleaning your veins or doing some other sort of suturing. And so the idea will be to really try to shrink medical tools to a scale that is super tiny and will cause the least amount of damage during the procedure. The cilia are interesting for various reasons. We think that we can create standalone devices. So we've shown how to link these cilia to the microchips. And so you could have a device that maybe a centimeter on the side that you would take into the field. You wouldn't need any microfluidic pumps or anything else attached to it. You just sort of put a drop of water on there, and in sunlight it would do the mixing and analyzing of the material. So that's an exciting area. And we're also thinking about the field of flow chemistry, where people, instead of sort of mixing chemicals in a bath with a stir bar, now sort of flow things together on much more refined scales. And here the cilia could be used to further optimize the chemical reactions, changing the flow rates and local interactions of the chemicals. So those are some of the ideas. And I would say that, nothing is simple at this scale. I mean, once you know how to do something, then you can do it again. But developing something new at this scale is hard. And so we're always super cautious about which challenges we take up. And, we want to make sure that we're we're doing something that's worthwhile. So it's a challenge, but I think there are some nice application domains that we can go after.
Yeah, I can imagine that you have to kind of figure out what, to do next with it. But the medical tools, like especially like bronchi or passing blood-brain barriers and delivering, something somewhere where you usually have like issues going in without damaging too much, or you just don't have these tools that are small enough to scrub off, I don't know, the bronchi of people with COVID, or delivering like anti-inflammatory stuff where they need it. I would imagine, but how do you get them out of there afterwards? Um, is there
Right.
Do they
So
just self-destruct maybe after a while, or?
right. So if they're at the end of a fiber, you just remove the fiber. If they're on their own, even powering them becomes a challenge, right? Like if these things are light operated, you may not be able to get enough light into the body to do something. And so in those cases, you might want a magnetically actuated robot. And, they're not very big. Again, 100 microns is pretty small. So these are things that can be flushed by your body. But all of that has to be sort of, there have to be studies that track these robots as they go through your body, and you have to see where they end up in your in the flushing system, if you will.
Yeah, thank you so much. I want to pass the mic on everyone else that waited so patiently. So Daniel, Victoria, Eli, Dr. Shah, Ryan, please go ahead. Yeah, Dr. Shah, go ahead.
Yeah, thank you so much. That was really, exciting research, and thank you so much for sharing. As you mentioned, partially, my thinking was around the emerging of the devices, and that we have the mimicry of the biological perception. And so, for example, some of them, we have lots of the researches around that. And I was just wondering if we want to think about emerging devices and having some protocols, also by considering the performance optimization or cost control and all of those things, plus the, for example, data redundancy, how you see the possibility of that. And I was just thinking about that part.
Yeah, I mean, I'd say that there's a lot of technology that we first have to develop before we see these sort of more sophisticated applications. If you want this device to capture data, you need sensors on board. Figuring out how to integrate chemical sensing with electronics is a really big problem. Like nobody knows how to do that really well. There are things like ion sensitive field effect transistors, but they're pretty crappy for really doing specific chemical detection. So there's a lot of science to develop here. I think what's also interesting is that all of the electronics that I've shown you here is using 180 nanometer line widths. And right now, the best devices out there use a 2 nanometer line width. So there's a lot of room for expanding the electronic capabilities on these devices, right? There's, again, this amazing amount of development in terms of the electronics. And what we're essentially pointing out is that all of those electronics can now be integrated with moving components, in the future, little sensors, cameras that can be pointed in different directions, uh, you know, elements that can be used to cut, local environments or locomote the chip to a different location. All that's doable. But in terms of the kind of sophisticated things that you're talking about, it's going to depend on the engineering applications.
So there is not a certain algorithm right now, based upon the researches that you just shared with us, that we can rely on for all of those purposes.
No, there isn't like a set out of the box thing that you can buy. What we would like to do is, now that we have this platform, we would like to set up a a process where researchers at other universities could go in with us on fabricating their own electronics. So the idea would be that we would sort of have a fabrication process where people submit their electronics designs, and then we would all share the cost of the fabrication. Each group would get like a quarter of the wafer for their own devices. It would allow you to reduce the cost per fabrication run, and it would allow other people to get involved. And then all of the techniques that we did to essentially fabricate these robots, you could imagine transferring those, or at least showing people how to do it at the CNF, and then asking or figuring out what the comparable tools are at their institutions. And so then there wouldn't be as much of an overhead in terms of developing the header integration of the electronics with the actuators. And so if people have those, then it becomes more of a plug and play, system or platform that people could do interesting development on. And as those become more and more sophisticated, then you can imagine, a more standard library of tools that you would put together to do your various engineering applications.
Yeah, for example, the environmental assessment patches, that they can be related, and we're going to have the access to the sensory data. It can make it very complicated. Thank you so much. I'm passing the mic to the next person.
I had a follow-up comment. Ideally would be that the robots assemble themselves robots. So is that maybe the next thing to make it cheaper, to create robots that can do this?
Yeah, I mean, most likely, we're using fabrication processes. So the idea of the gray goo, robots that manufacture other robots, and next thing you know, the world is flooded with microscale robots that are oozing everywhere. That's not going to happen. Most likely, these robots are going to be able to structure and mold the environment around them. So something like hundreds of thousands of these robots going around a petri dish trying to, clean up or mold or arrange a surface, maybe an artificial tissue or organ that you're trying to grow, something like that, but not really building themselves. Because again, it's hard to imagine how a robot would use atomic layer deposition, or how it would implement atomic layer deposition on its own. These are really things that you need, these fabrication tools to do.
How will they get their energy and how do they process it?
Yeah, again, that's a great question. So one of the things that we're doing, well, what we're doing now is we're just using photovoltaics. So they have solar panels on board. But you can imagine other things. I mean, there could be batteries on board. Those would give you on the order of 10 minutes of operation. It's not a lot, but it's something, and there may be engineering purposes for which that's enough. There are other ways of thinking about it. You could have magnetic elements that you could essentially use external magnetic fields to crank, and those would provide the power. So that's something that we've thought about. And that would allow you to operate these machines deep inside the body where magnetic fields can penetrate. Chemical energy is another one. That's an interesting area. There's a lot of energy that you can harness from the environment. So, for example, in the air-based actuators, you can just flow gas, and that's enough to the surfaces essentially catalyze reactions, and the energy emitted from the catalysis from the chemical reactions is enough to, allow you to bend these materials. So all of these are possibilities.
So a couple of comments going back to the previous issue about robots assembling themselves. I've actually been working in the field of molecular nanofabrication and related robotics involved in that. And so, there is this, ultimately, systems that can programmably fabricate a wide range of things, including everything that goes into those systems, really puts us in a totally different ballpark in terms of industrial and post-industrial production and manufacturing, and opens up a whole bunch of other things. But there is this issue of how do you safely control it? Actually, the thing that I really appreciated in your presentation was that essentially the simpler control system for walking was a finite state machine. And that actually really is the best choice for controlling things, because not only does it take up less real estate or fewer components, but you can, at least if you design it properly, you can design it such that you can comprehensively enumerate both the state space and the state transition space. And the important thing about this is that then you can show that you've designed a system such that it's not gonna ever do anything surprising, right? Simply because its complexity is bounded, and you've gone through every possible combination, and there's no gray goo apocalypse in any point in the state space. Similarly, though, thinking about it as you were going through the presentation, I think this is actually something that could also be applied towards swarm systems, and you could arrive at kind of a landscape with defined features, and that might actually be a really interesting way of both making swarms more tractable, but also you now have quantifiable metrics for the complexity of swarms and swarm behaviors. I just wonder if you had any comments on any of that.
Yeah, I mean, I think in general, I share your lack of worry that these things are going to go out of control. They're so simple that we're not worried about them doing something that we don't understand, at least at this point. You could imagine, as the circuits get more sophisticated, that you would put in some sort of rudimentary neural net embedded in these electronics, and then these things could learn how to do certain things. But again, I think we're still in the very early stages, and everything is still very primitive. In terms of swarms, I think that's also something that I mentioned a little bit. It's really, we have a proposal out for creating a 1 million robot swarm, and you really have to think a lot about how you're going to implement coordinated behaviors in these in robots, in swarms with that many robots. You can't individually address each robot and give each robot instructions. So you want to have local autonomy. You want to have the robots be able to sense and interact with one another, maybe have emergent behaviors that come out of the synchronizations of these robots. So there's a lot that we're trying to research and explore in terms of how, collectively 1 million robots, 100,000 robots could act as a cyber physical system, that's connected to some sort of eye in the sky that's giving it commands, but again, in a way that is more of like a blanket, giving the entire swarm instructions rather than individually addressing each robot. So those are the kinds of things that we're thinking about, and we'll see what happens.
Yeah, so just to follow up on this specific point, it's where you have two things. The potential for things going wrong, having significant consequences, number one, and number two, where you've increased the complexity of individual components such that it becomes difficult or impossible to enumerate the state space, that things could get problematic. Um, so that's kind of like a phase boundary between what we can definitely say will never pose a problem, and where we would at the very least need more focused analysis to tease that apart.
Yeah, I mean, so in terms of putting these things in places that they could be doing damage, I mean, if you have one of these things going around in your brain, ripping the whole thing apart, even if it's doing something simple, it could be damaging. So there is some obviously some caution that you have to take. And in terms of the complexity of their state space, I don't think we're anywhere close to that boundary.
Yeah, certainly agree with the last point.
Yeah, thank you so much for these questions and this discussion. I think it's really important to discuss it. Yeah, it was great questions, Eli. The other thing I wanted to maybe just mention, because there was the machine learning part mentioned how to do it. We had a guest speaker here, Dr. Onan. They made this nanoscale ionic programmable resistors for analog deep learning. Maybe that would be a good person to collaborate with. I don't know, to have this nanoscale machine learning devices. Or do you know already his work, maybe?
I don't, but it's a very exciting area, so I'd be interested in finding out more.
Yeah, wonderful. And I wanted to check in with you, how much time you have left, because we've been going over an hour now, so I wanted to check in with you to not take too
Yeah,
much of your time.
I think we have to wrap up soon. I have a couple of kids waiting at home that I better not keep for too much longer.
Yeah, so
Sorry, I cannot. Something broke up, I think.
Yeah, you dropped out, Katerina. She's probably having issues with her connection.
Technical issues, right. All right. I'm not hearing much more, so maybe we leave it
One
there.
question that I had, that was about the drug delivery.
Oh,
If you have
yeah,
shortly, you can explain about that.
sure. What was the question?
About these devices that you just introduced with the use of the drug delivery and making the hybrids, and how they might be beneficial for the biohybrids and
Yeah, I
those kind
mean,
of things.
so the idea of transporting cargo, that's easy to imagine. You can have robots who pick up cargo from one location, transport them, and send them to another. In most sort of microscale robotics proposals, you'll see people trying to do this with microscopic particles that have, that sort of use the body's natural pathways to get around, and then maybe attach to cells via antibodies or things like that. And here you could imagine, you know, really having a robot that sort of sniffs a molecule and goes upstream until it finds the source and delivering the drug in a very deliberate fashion. Now, I don't know if we would do that inside the body. That's certainly a long ways off. But thinking about doing that on the Petri dish, that's certainly something that's in our sights.
Yeah, they call it immunobots. Yeah, they are using that. So, Victoria, can you hear me? I mean, I think we can just wrap it up.
Yeah, sorry. Can you hear me now?
Yes.
Oh, I don't know. My connection must have been bad for a second. Okay. Thank you so much. I'm sorry I didn't hear in between, but I heard the end with Dr. Shah. So again, thank you so much for coming, and maybe you'll come back one day and talk about more exciting research you do. We
Excellent.
put. I will certainly follow your work, and I guess a lot of people here will. And yeah, we wish you a lot of grants and a lot of great students to help you with your work and collaborators. So yeah, thank you so much, and enjoy the rest of your evening, and happy
Excellent.
holidays.
And, if people have any questions, please feel free to get in touch with me by email. I'm at Cornell University and not very hard to find.
Oh, that's very kind of you. Thank you. Yeah. So yeah, and people can reach out to me if you don't find the email. I can surely make the connection. So perfect.
Okay. Thank you very much again for hosting this, and I appreciate the opportunity to speak with you and the folks in the clubhouse.
Yeah,
Thanks for the
wonderful.
talk. It was really interesting.
Great. Excellent.
Thank you. Thank you very much.
Bye-bye, everybody.
Bye. And thanks.
Bye bye. Thank you.
Yeah, thank you. And thank you everyone for coming, participating, asking questions. And if you like rooms like this, follow the club. We'll have another room. We have more rooms next week. So we'll have Dr. Q talking about gene expression for caste differentiation and ants. I don't know if you know, but ants have kind of different type of work to do in the society, and they also look very different. Yeah, the Dr. Q is working on studying that and how that works. And apparently he found mechanisms in gene expression, how in one ant society there are different type of ants. And then on Tuesday, Dr. Ando will talk about how life adapted to oxygen. It was actually quite a shock for life when oxygen came online, and it was theorized to have been actually quite toxic, and like a lot of life actually died even, probably. And yeah, he will talk about that. And Dr. C will talk about personalized drug discovery omics, data integration, which is a really interesting topic and paper they published. And on Friday, Dr. Luke will talk about space and how to find water-rich worlds in space. Yeah, it will be an exciting week. Next week, end of December, we kind of have a little bit of break for the holidays, so we'll have rooms like mid-December, but then after the 20th, more or less, a little bit of break, and then we have room starting in January again. So yeah, that's for the announcements. And thank you, everyone. Thanks, Victoria, for the interview, Dr. Shah for moderating too, and everyone, thank you. Okay, I'll
Thanks,
close the room.
Katerina.
Thank you. I feel like my goodbyes are getting longer and longer. It's my Portuguese thing, like to have a hard time ending. So
Don't
okay.
go. Don't go.
Okay, 3, 2, 1. Bye, everyone. Thank you.